This next example is a half-life problem. So if we know that carbon-14 has a half-life of 5,728 years, then we want to be able to write down an equation that models the amount of carbon-14 after a certain number of years. So let's use this information that if you start off with a certain amount of carbon-14, and we assume that the amount can be modeled by an exponential function, we want to know, well, we're just going to assume that our equation is written in this way. And we want to use this fact and the fact that at time t equals 5,728, we have half of that amount left. So original amount times a to the power 5728 equals half of the original amount. And we could have used that shortcut where we set the equation equal to a half without the leading coefficient, because if we divide both sides by a naught, then it cancels on both sides, and we're left with a to the power 5728 equals 1/2. And now, in order to solve for a, I want us to think of, suppose I had something like a squared equals 4. You would solve that by taking, say, the square root of both sides, or raising both sides to the power 1/2 to get a equals the square root of 4, which is 2. Or suppose if I had like a cubed equals 8. I could solve that by saying, what number cubed is 8? Or in other words, taking the cube root or the 1/3 power of both sides. To get a is the cube root of 8, which is 2. Anyways, these examples are to show that if you have a raised to some power equals a number, you can solve that by taking both sides to the power 1 over that number, 5728. So this will be 1 over 5728. So what we have is that the base a is going to be written as 1/2 to the power 1 over 5728. Now, you can use this as like an exact number, or you could write this with a negative exponent, like 2 to the power negative 1 over 5728. You could use that. These are equivalent. Or sometimes it's useful to write that as a decimal. So if I wanted to, I could also say 1/2 to the power, and put it in parentheses, 1 over 5728. And I can get this number out. So usually I wouldn't use a decimal approximation because that introduces like an error into your calculation, and you don't want that error to like propagate and get bigger and bigger. But sometimes it's useful to have that approximation. I would say let's use 5 or 6. Let's do 6 decimal places. So 99987, and then maybe I'd bump this up to a 9. So 0.999879 approximately. So again, it's up to the situation that you're in. I would probably prefer to use this as my A, but sometimes you can use a decimal approximation. All right, let's go on. Give the equation of the exponential that models the decay of 300 grams. So this is my initial amount of carbon-14. So I'd say, okay, I know A of t is going to be the initial amount times a to the power t. And I'll use this as my A. So 2 to the power negative 1 over 5728 to the power t. So this is my A. And you can simplify that by saying 300 times 2 to the power, and then multiply these exponents. That would be t over 5728. All right, and then we can use this equation to answer some questions, like how long will it take for 300 grams to reduce to 200 grams? So here, I would set the equation. I would set it equal to 200. All right, I would divide both sides by 300 first, and that would give me 2 to the negative t over 5728 equals 2/3. And then actually, I'm going to stop here because I cannot rewrite both sides with the same base. So therefore, we cannot solve. Not solvable with elementary methods. So we kind of have to wait until section 7.5 until we can solve this problem all the way. All right, let's move on to this last problem. This is another example where you're going to have to create the equation that you want to use. In an effort to control vegetation overgrowth, 100 rabbits are released in an isolated area that's free of predators. So what that's saying is that you can just use the a of t equals a naught times a to the t. We can use this model to model the situation. And then 100 rabbits are released in that area, so that's telling us the initial amount of rabbits. Okay, that's our a naught. So let me just kind of fill in that information as I go. I've got 100 times a to the t. All right, after 1 year, it's estimated that the rabbit population has increased to 500. Assuming exponential population growth, what will the population be after another 6 months? Okay, so a couple things here. First, we have to figure out, I'm using time t for time, but I need to think about how I want to, what units I want to use to measure time. I could let time be in years, or I could let time be in months. So notice that in this problem, we use both years and months. So you just kind of have to make a decision, and then you're going to have to convert the other unit. Maybe for simplicity, I might say, let's use months. Okay, the other thing I want to do is I want to think about the amounts that I already know. Like, and I'm going to make a table of values there. Like, I know at time 0, I've got 100 rabbits. And I know also after a year, I've got 500 rabbits. So 1 year, that's 12 months, right? So after 12 months, I've got 500 rabbits. And then the information that I want to know is what will the population be after another 6 months. So 6 months after that year, that would be 18 months. And this is what I want to solve for. I want to know what's the amount at that time. Okay, so now I have my data kind of here in a table. Let's kind of use that table to solve some of these questions. So I've already used this data point by setting the coefficient equal to 100. Now let's use this data point by plugging 12 in for t, setting the equation equal to 500. So I've got 100 times a to the 12 equals 500. All right, let's go ahead and solve for our base. Divide both sides by 100. You get a to the 12th equals 5. And then I can raise both sides to the 1 over 12th power to get that a is 5 to the power 1/12. All right, so this is great. Now I know what the base is, so I can go ahead and rewrite this equation. The amount after time t should be 100 times a, which is 5 to the 1/12th power, to the power t. And you can even simplify this by multiplying those exponents. That'll be 100 times 5 to the t over 12. All right, next thing we want to do is now use this data point, plug in 18, and figure out what we would get for the output. So a of 18 would be 100 times 5 to the power 18 over 12. So we get 1,118.03. So I think what I'm going to do is I'm going to round it to the nearest whole number so that I can tell you that many whole number of rabbits. I'm not going to have like a decimal amount of rabbits here. So I've got approximately 1,118 rabbits. We can even fill that into the chart back here. Alright, so notice what we had to do. In this problem where we were not given any equation, we had to write down a basic exponential equation, organize our data in a table, figure out what our variables represent, right? Okay, now use the data in our table to figure out what the base would have to be. Rewrite the equation with all of that information, and then plug in the other information from our table and to answer the question that was asked.